Okay, this is the final video on double slit interference or double slit diffraction patterns. And what we ended up with on the last video, we came up with the relationship that the difference in path length, which we calculated to be d sine theta, when that value, where d remembers the spacing between the slits, and theta is the angle that the light is coming from the slits with respect to the horizontal, when that value is equal to 0, then you're right in the center here. In other words, there's no difference in the path length between this ray and this ray of light when it's in the center. When it's in the upper direction, which is somewhere up here, then the difference is a positive number of wavelengths. It could be 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths. That means that the lower one travels that many wavelengths more than the upper one. And whether it's 1, 2, 3, or 4 doesn't matter, because at the screen they're going to be in phase with each other. They're going to both be a maximum at the same time and a minimum at the same time, which means they're going to interfere constructively and you'll get a bright spot on the screen. Similarly, when n is negative, you're going to be down here. And this case results also in the similar bright spots pattern on the screen. It's just that in this case, this wave, this line here travels further than this line, the waves on that line. Okay, so this is the relationship. If there's one take-home relationship for the double slit pattern, it's this. And then it's just a matter of interpreting that, and that's what I hope to show you in the next slide. So we have d sine theta equals n times lambda. Now n is often called the order. It can be 0, 1, 2, 3, or 4. So when you see a bright spot on the screen, the order 0 bright spot is the one right in the middle. The order 1 or minus 1 spot is the one right next to it, etc. 2 is 2 down from the middle, up or down, whether it's plus or minus. The angle theta is a little bit cumbersome for us when we're on a screen. Let's say we have a screen over here, like what you're going to have in lab, and you have a couple slits here, double slit pattern, resulting on the screen. The angle is this angle measured from here. That's not a very convenient angle to measure with a protractor, because you can't measure these beams of light accurately and all that. All you're really going to see are bright spots on the screen that look something like that on both sides. So the angle of this value here, if we know this distance here, which I'll call x, as I've been calling, and we know this distance here, which you can measure. In your lab, I think you're going to have it horizontal, although you could rotate your slits to make it vertical. I'm going to call it vertical right here, just so that I can show you on this video, on this two-dimensional screen that I'm drawing on. But x here is this distance across, and it's also approximately this distance here. And you may say, wait a second, that's not x, that's a hypotenuse. But remember, we're assuming that the screen is much further than the distance here, and I'm also assuming that theta is small. And I've showed you this earlier in the semester, much earlier, but that if the angle is small, then the hypotenuse is very similar to the length that's directly across the screen here. Okay, so I can take the hypotenuse to be x, in this case, without too much of a concern. It'll be fine. Later on I can't do that if the angle gets bigger, but for theta small, which is what we're going to see here, you're going to see a pattern that's only a few centimeters across when you do this with just two slits in lab. Then we can say the sine of theta is equal to the opposite side divided by the hypotenuse, which I'll take to be x, for the reason I just mentioned. So if you plug that into here, it makes the expression much simpler. You don't have any angles to deal with. So it's going to be d times y divided by x equals n times the wavelength. I'll write that out here. D times sine of theta is y over x equals n times the wavelength. So just to define what the terms are, slit spacing slit to screen. I might call that H. I don't recall what I called that in the video. This is the Y is the location of the bright spot. Now, there's a lot of bright spots, as you'll see in lab, and if it's the first bright spot, then n is 1. If it's the second bright spot, so let's just say this is y1, then n equals 1, or it's really y sub n. It's the bright spot that corresponds to the given fringe number. So if you're 0 wavelengths across, then it's y0. So when n is 0, then it's y0. When n is 1, I'm going to call it y1. When n is 2, it's y2. This is to distinguish the many bright spots you'll see. So depending upon what we're interested in, we can use this equation to calculate what it is. And often it's the location of the nth bright spot. And that's kind of like what you're going to do in lab, and I'll just do that for you. It's just simply calculating the value of a given position of a given bright spot. It's going to be equal to n times the wavelength times x divided by d. This is for a double slit interference pattern. All I did was I solved that equation to come up with this. Remember, n is an integer. Could be -1, 0, 1, 2, 3. It's an integer, which tells you how far from the center point, that center bright spot, are you. And then y is the position of that bright spot from the center, the distance in meters. Okay? Lambda is the wavelength of the light. X is the spacing between the double slit and the screen itself. And D is the spacing between the double slits. Okay, so this is an interesting pattern that Young first saw. A guy named Young, when he did this, he didn't have lasers back then. You get to have lasers. It's much easier to see with lasers. What's interesting is if you change the wavelength of the light, if you use red light instead of green light, then the spacing will change. And that's what you're going to actually see and measure today in your lab. Okay, take care.